Hi everyone, this is going to be the 7th lesson on the topic of chemical reactions for GCSE chemistry students. In this lesson we're going to be taking a look at electrolysis in more detail. So before we get started, as always, let's take a look at the learning outcomes for this lesson. So once you've completed watching this lesson video, and if you're watching it from within this GCSE chemistry course on my website, once you've completed the various questions that will pop up at intervals throughout this video when the video pauses, and also the end of lesson quiz and other learning activities on this lesson's page, you should be able to do the following things. So in this lesson we need to look in more detail at electrolysis. It's something that we've encountered in previous lessons, but in this lesson we're going to be expanding upon what we've already talked about. So firstly, recall that electrolytes are ionic compounds either in the molten or liquid state or in the aqueous state, dissolved in water. We need to describe electrolysis as a process where electrical energy from a direct current power supply is used to split apart a compound into its elements. So in other words, what we're dealing with here, as far as chemistry is concerned, is a decomposition reaction. We need to explain the movements of the oppositely charged ions in the electrolyte during electrolysis, in which positively charged ions called cations will move towards the negatively charged cathode. And conversely, negatively charged ions, which are referred to as anions, will migrate towards the positively charged electrode, the anode. We need to look at various examples of electrolysis, various different types of electrolytic reactions, and explain the formation of the products in terms of the transfer of electrons to or from the ions in the electrolyte. And in doing this, in various examples, we're going to be looking at both the full chemical equation that describes the electrolytic decomposition and also the half equations, which describe either the reduction or the oxidation which are happening at the two different electrodes. So obviously, we are going to be revisiting the concepts of reduction and oxidation because, as we said before in the lesson on redox reactions, electrolysis is an example of a redox reaction because both reduction and oxidation are happening simultaneously. So we've got lots to get through. There are a number of different examples, including the electrolysis of copper sulfate solution and various others that we need to get through. Now, again, I'm joined by a number of students via the Zoom client who have asked a number of very interesting questions prior to this lesson. I will be addressing those in the Q&A session at the end for you guys. But if you're watching this as a recording and you have any questions about this lesson, as always, you can simply log into the website, and if you're registered for this course, you can navigate to this lessons page, and you can either leave your questions as private messages to me, in which case I'll respond to you privately with an answer, typically within about 24 hours. Alternatively, you can leave your question in the live chat, perhaps start a discussion with other students, and I will respond there as well. If you're watching this elsewhere, such as on YouTube, then by all means, if you have any questions concerning electrolysis, then go ahead and type those in the comments, and I'll do my best to get back to you there as quickly as I can as well. Okay, we've got lots to get through, so let's get started here. So before we start to talk about electrolysis in more detail, we need to understand something that we call ionic equations. Ionic equations are a form of chemical equation. In all chemical equations, as we've seen so far, the reactants are written on the left-hand side of an arrow and the products on the right-hand side. So an example of this would be the reaction of sodium metal with chlorine gas to form sodium chloride, as we see here. On the left-hand side, we have the reactants, and on the right-hand side, in this case, we only have one product. But ionic equations will also require you to know the charges, the electrical charges on the ions which are involved in the reaction. You also need to include state symbols as you would with any other chemical equation. So a little reminder here about state symbols. So there are 4 state symbols that show the physical state of the reactants and products. As with any chemical equation, you would also use these in ionic equations. So an L means liquid, an S means solid, G means gas, and AQ stands for aqueous solution, which means dissolved in water. So state symbols should always be written in brackets to the right after each reactant or product formula, as shown here. So let's take a look at ionic equations now. So sodium chloride is an ionic compound, as we've seen, that's composed of oppositely charged ions, sodium ions, which are Na+, and chloride ions, which are Cl-. Now it's formed by burning sodium metal in chlorine gas. So sometimes the ionic compounds formed as a result of a chemical reaction can be written in their ionic form. So for example, instead of writing sodium chloride as NaCl and the solid state symbol, we can also write this as Na plus Cl minus and the solid state symbol. This simply tells us that what we're dealing with is an ionic compound composed of these oppositely charged ions in a 1-to-1 ratio in this case. So here again is the chemical equation to describe the formation of sodium chloride from its elements. Now when this equation is written in an ionic form, it looks like this. So the word equation again would be the same, but in this case the ionic equation would look like this. The ions comprising the sodium chloride can also be written separately. So again we have the same word equation, but in this case we can also write it like this. So try balancing the following equation and then writing it in an ionic form. So here is the word equation. I'm going to pause here and let you guys have a go at writing down the balanced symbol equation. Now again, if you're watching this video on my website as a recording, the video will pause and you'll be presented with an interactive question for you to answer. If you're watching this elsewhere, then by all means pause the video and see if you can work out the balanced symbol equation for this reaction. Okay, so here's the balanced symbol equation. Sodium hydroxide has the formula NaOH, magnesium chloride has the formula MgCl2, sodium chloride we've seen is NaCl, and magnesium hydroxide is Mg and OH in brackets with a subscript 2. So to balance this equation we need 2 moles of sodium hydroxide reacting with 1 mole of magnesium chloride to form 2 moles of sodium chloride and 1 mole of magnesium hydroxide. So now let's see if you can write this same balanced equation in its ionic form. Again, I'm going to pause and let you guys have a go at this for yourselves. And again, if you're watching this on my website, the question will pop up. If you're watching this elsewhere, then go ahead and pause the video and see if you can work this out. This time, I'm not going to include state symbols. I'm simply going to write down the balanced ionic equation in a moment. So have a go at this for yourselves. Okay, so both of these are ionic compounds. They're composed of unipositive sodium ions, a OH minus ion here. So for this compound we have Na plus and OH minus. For this compound we have Mg2 plus and Cl minus, but we have 2 chloride ions, 1 magnesium ion. Here we have 1 sodium ion and 1 hydroxide ion for every unit of sodium hydroxide, but we have 2 units of sodium hydroxide. So the left-hand side of the equation is going to have 2 sodium ions, 2 hydroxide ions, 1 magnesium ion, and 2 chloride ions. Now if we look on the right-hand side of the equation, we're going to get the same numbers of sodium ions and magnesium ions as we had on the left-hand side. But in this case, we also have 2 chloride ions and 2 hydroxide ions as well. So the ionic equation for this is going to look like this. So as we can see here, we can either write a balanced symbol equation, or if the reactants or products are ionic, we can split them into their component ions like this to form the ionic equation. So let's take a look at electrolysis and see how we put these principles of writing ionic equations into practice here. So to remind you, electrolysis is the chemical decomposition of an ionic compound by direct electrical current. Now this is not always the case. Sometimes we will decompose a simple covalent compound like water into its elements. So more generally, electrolysis is a chemical decomposition of a compound into its elements by means of the use of electrical energy. And the device that we perform this reaction in is called an electrolytic cell. So this animation represents a general electrolytic cell. You always have an electrolyte, which is either a molten ionic compound or a ionic substance which has been dissolved in aqueous solution. Most of the time that's what you're dealing with when you're dealing with an electrolyte. It is a substance that contains oppositely charged ions which are free to move in either the liquid or the dissolved state. You also have a source of direct electrical current. In this case we have an electrical cell here. You have a positive electrode called the anode. This is where electrons go into the circuit. And you have a negative electrode, and this is where electrons flow out into the electrolyte. This is called the cathode. Now, within the electrolyte, you have positively charged ions and negatively charged ions. The positively charged ions, which are called cations because having a positive charge, they are attracted to the oppositely charged negative cathode. In contrast, the negatively charged ions are referred to as anions because they are attracted electrostatically to the positively charged anode. And so this is a diagram of a generalized electrolytic cell. Now typically, not always, but typically the electrodes are made of either metal or graphite. Graphite is very useful because it's rather cheap, it's widely available, it's resistant to high temperatures, and it's also electrically conductive. So the compound that we are electrolyzing must be either in the molten or the aqueous state in order for electrolysis to take place, because the ions in both of those states are free to move to the respective electrodes that they're attracted to. So once again, negative ions are attracted to the positive electrode, the anode, and so they are referred to as anions. Positive ions are attracted to the negative electrode, or the cathode, so they're referred to as cations. So let's take a look at what's actually happening at these two electrodes separately here. So let's start with the anode. At the anode, the anions will surrender their electrons, which then pass around the circuit driven by the direct current power supply. So the anions, because they start off negative and they're giving up their excess electrons, the anions become electrically neutral atoms. So again, in general, what's happening is you have a negatively charged ion, let's just call this Y-, it is giving up its electrons. If it has more than one negative charge, it will give up more than one electron. But essentially, by giving up its excess electrons, these anions are becoming atoms with a neutral electrical charge. So here we can see that electrons are being removed from the anions, and so we can say that this is an oxidation reaction. So at the anode, at the positive electrode, oxidation takes place. Now in contrast, at the cathode, at the negative electrode, we have the cations, the positively charged ions, will have electrons added to them. So if they start off positively charged, let's call them X+, they will gain electrons such that they become neutral. So in this case, if the cation has a single positive charge, each one will gain one electron to form a neutral atom. If it has two positive charges, each one will gain two electrons to form a neutral atom, and so on. But in all cases, as we can see here, electrons are being added to the cations, and so this again matches the description of reduction. So let's take a look at some examples. Let's start with the electrolysis of molten sodium chloride. Now what we mean here is sodium chloride, which started off as a solid, it's been heated to its melting point and has melted to form a liquid. So when sodium chloride is melted, the molten sodium chloride becomes separate chloride and sodium ions in the liquid state. Now, half equations are equations which are used to show what is happening at the positive and the negative electrodes separately. Now, as always with any kind of chemical equation, both sides of the equation must balance. So during electrolysis at the anode, you have, in this case, the negatively charged ions giving up their electrons to form atoms. Now, if you form chlorine atoms, as we saw before in previous topics, will form pairs where they covalently bond with each other to form chlorine gas molecules, Cl2. So at the anode, we have oxidation taking place where chloride ions will each give up an electron, but they will do so in pairs so that those two electrons go into the circuit and will leave behind a chlorine gas molecule. So we have the formation of chlorine gas at the anode. Now at the negative electrode, at the cathode, we have sodium ions which gain electrons. Now, since we have two electrons which have flowed into the circuit, those two electrons will flow around the circuit. They will be pushed by the direct current power supply from the anode, where they were taken from the chloride ions, to the cathode. At the cathode, those two electrons will each be given separately to one sodium ion. So two sodium ions will be needed to bond with or to accept these two electrons, and this will form two atoms of sodium. Now this will form a deposit of sodium metal on the cathode. So let's visualize this with an animation. So here we can see at the positive electrode, chloride ions are giving up electrons in pairs to form Cl2 gas. At the negative electrode, sodium ions, are accepting electrons to form solid sodium metal. So this is what's happening in the electrolysis of molten sodium chloride. So we can see here we started with sodium chloride, the compound, and we've ended with the elements chlorine gas and sodium metal. So what happens then when we electrolyze not molten sodium chloride, but sodium chloride in aqueous solution? So a solution of sodium chloride, sometimes called brine or salt water, can also act as an electrolyte because in the aqueous state, the sodium ions and the chloride ions are free to move through the solution. Now, during the electrolysis of brine, which is aqueous sodium chloride solution, there are actually three important chemicals which are produced as a result of the reaction. So here is the overall equation that describes what's going on. So in this case, you don't just have sodium chloride present, you also have water molecules which are present in the sodium chloride solution. These will also react in the electrolysis, as we'll see. So in this case, you form sodium hydroxide in aqueous solution, you form hydrogen gas, and you form chlorine gas. So in the case of the electrolysis of aqueous sodium chloride solution, the sodium chloride will contribute sodium and chloride ions to the electrolyte, but in addition to that, the water molecules will also provide hydrogen ions and hydroxide ions. So in the electrolyte this time, you actually have four different kinds of ions present. The positively charged hydrogen and sodium ions are both attracted to the cathode, to the negative electrode. However, in this case, the sodium ions stay in the aqueous solution. So what's happening actually at the cathode is that the hydrogen ions are gaining electrons to form hydrogen gas. Now, both the chloride and the hydroxide ions, in contrast, are attracted to the positive electrode, to the anode. But in this case, the hydroxide ions stay in the solution, and it's the chloride ions which give up their electrons into the circuit to form chlorine gas. So once again, the half equation is this for what's happening at the anode. The chlorine gas will have traces of oxygen within it, which is caused by the presence of hydroxide ions at the anode. So some of those hydroxide ions, a very small amount of them, will react at the anode to form oxygen gas and also water molecules, and they will submit their electrons into the circuit. So this means that the electrolysis of sodium chloride solution, or brine, produces hydrogen gas, chlorine gas, and leaves behind a sodium hydroxide solution. Now, all of these are important chemicals which are used in a number of different chemical reactions and are very useful in industry. So again, let's visualize this with an animation. So here we have sodium chloride solution. This is brine. So as you can see here, you've got sodium ions, you've got chloride ions, hydroxide ions, and hydrogen ions. But as you can see here, the sodium ions and the hydroxide ions essentially stay in the solution. At the positive electrode, at the anode, the negatively charged chloride ions, which are attracted to this positively charged electrode, will give up their electrons in pairs to form Cl gas, which is given off as bubbles at the anode. At the cathode, at the negative electrode, the hydrogen ions, which have the opposite charge, are attracted to the cathode, and they will absorb, they will accept electrons again in pairs to form H2 hydrogen gas bubbles. So here are a couple of examples of half equations for you guys to have a go at, and I will pause after each one. So here is the first one. We've got nitrogen. So how many electrons need to be accepted by this nitrogen gas molecule to form two N3 minus ions? So I'm going to pause here and let you guys have a go at this one. All right, so the general consensus seems to be 6. So let's see if you guys are right. Yes. So the way that you can think of half equations like this one is just like a regular chemical equation, the number of atoms of each element must balance on the left and the right. So we can see here on the left we have one molecule of nitrogen gas containing 2 nitrogen atoms chemically bonded together. On the right hand side we have 2 separate N3 minus ions. So the nitrogens balance. But the other thing that needs to balance in any chemical equation or half equation is the total charge on the left and the right hand sides. So if we started with 2 N3 minus ions, we have a total of 6 negative charges on the right hand side, which means we need 6 electrons to make up those 6 negative charges on the left. So have a go at this one. So we have SO4 on the left-hand side. How many electrons do we need to add to this to make a sulfate ion? All right, so fairly straightforward this one. You have a total of 2 negative charges on the right-hand side, and the only thing with negative charge on the left-hand side are electrons, we need 2 electrons to be added to this SO4 molecule to make an SO42- ion. How about this one? Okay, so we have an oxygen molecule containing 2 oxygen atoms chemically bonded together. This is electrically neutral. We're adding electrons in such a way as to produce 2 oxide ions. Now the oxide ion, each one is di-negative. It has 2 negative charges. So in total we have 4 units of negative charge on the right-hand side, which means we need 4 electrons on the left-hand side. Have a go at this one. Okay, so this one's fairly straightforward. We have a single sodium atom on the left-hand side. This is electrically neutral. On the right, we have a sodium ion, which is positive. So to make the right-hand side electrically neutral, we need to add this to 1 negatively charged electron. Now, if you were writing this as a half equation, of course, you wouldn't use an equal sign. You would use an arrow if this was actually a half equation. But again, you wouldn't necessarily write a 1 in front of the electron. You can simply write E- just on its own. Okay, let's try another one here. So have a go at this one. Okay, so this one we have a magnesium atom on the left. It is electrically neutral, and so we have 0 charge on the left-hand side. On the right-hand side, we have 2 positive charges on this single magnesium ion here. And so to make the right-hand side electrically neutral, we have to add 2 electrons. What about this one? Okay, another fairly straightforward one. So we have OH on the left here. This is electrically neutral. And we have OH-, a single negative charge on the right-hand side. So on the left, to balance the charges, we need 1 electron. Okay, let's try another one. Okay, so in this case, we have a hydrogen gas molecule here, H2, 2 hydrogen atoms chemically bonded together in 1 molecule. On the left-hand side, we have 0 charge. On the right-hand side, we have 2 hydrogen ions, each of which has 1 positive charge. So we have 2 positive charges here. So to balance the charges, we have 0 charge on the left. We have 2 positives here. To make this neutral, we need 2 electrons. How about this one? Okay, so we have an aluminium atom on the left-hand side of the equation. We have 0 charge in total over here. On the right-hand side, we have an aluminium ion, Al3+, 3 positive charges. So to make the right-hand side electrically neutral, we need 3 negative charges. Okay, well done. Let's move on. So we need to take a look at some more examples of other salt solutions which can be electrolyzed. Now, problems can arise when using aqueous solutions of electrolytes because of the presence of water. If there are 2 types of cation present, 2 types of positive ion present, then a competition reaction will take place at the negative electrode at the cathode. Now, the relative positions of the metal and the hydrogen from the water in the reactivity series will determine which element is formed at the cathode. So to remind you, here is the reactivity series. So the element which is lowest in the table, lowest in reactivity, is the one that will be produced at the cathode. So as we saw before, in an aqueous solution of sodium chloride, which is being electrolyzed, sodium and hydrogen ions, 2 positively charged ions, will both be present in the electrolyte. But since hydrogen is lower down in the reactivity series than sodium, it is the hydrogen gas which is being produced at the cathode in that electrolysis. If we take another example, if we take, for example, silver chloride solution, silver and hydrogen ions, Ag+ for silver and H+ for hydrogen, will both be present in the electrolyte. Now, in this case, silver is lower than hydrogen in the reactivity series, and therefore silver metal will be produced at the cathode. Now, if an anion is present in an aqueous solution and it's a nitrate or a sulfate, you will also produce oxygen at the anode. If the anion present in the aqueous solution is a halide ion, such as chloride, iodide, bromide, so on, the halogen gas will be produced at the anode. So let's take a look at the electrolysis of an acid now. Let's take a look at what happens when you electrolyze an aqueous solution of hydrochloric acid. Now, hydrochloric acid solution is in fact a very good electrolyte. In aqueous solution, HCl will form two important ions, H+ and Cl-. Now again, because we're dealing with aqueous solution, water molecules can dissociate to provide hydroxide ions and more hydrogen ions in equal quantities in the electrolyte. So the dissociation of water is represented by this equation here. So in both cases, the hydrogen ions produced will be attracted to the cathode. At the cathode, the hydrogen ions will gain electrons to form hydrogen gas. The chloride ions, on the other hand, are negative, and they are therefore attracted to the positive electrode, to the anode. At the anode, they are oxidized. They lose electrons which flow into the circuit, and they do so in pairs to form the diatomic molecule chlorine gas. So the chlorine gas may have traces of oxygen within it because, again, we have the presence of hydroxide ions at the anode. Small amounts of those hydroxide ions can form oxygen gas and water molecules when they give up their electrons. The Ionic equation for that is here. That's the half equation. So this means that the electrolysis of hydrochloric acid primarily produces hydrogen gas and chlorine gas, whereas the electrolysis of extremely weak, very dilute hydrochloric acid will primarily produce hydrogen gas and oxygen gas. So again, let's visualize this with an animation. So here we can see the ions which are present, and I'm going to turn all the labels on this time. These are the ions present in concentrated hydrochloric acid. We have chloride ions which will be oxidized at the anode to form chlorine gas. It's the hydrogen ions which will be reduced at the cathode to form hydrogen gas, and the majority of the hydroxide ions will stay in solution here. So what happens when we electrolyze water then? So pure water is actually not a very good conductor of electricity. However, the electrolysis of water can be carried out by adding small amounts of dilute sulfuric acid to distilled pure water. So once we do this, we can actually electrolyze water into hydrogen and oxygen. So this is an example of, or rather this is a diagram of an electrolytic cell which is being used to electrolyze water. We have the two electrodes here which are graphite electrodes. They are immersed in water, and above each one of those electrodes we have a test tube which started off filled with water. As the gases, hydrogen and oxygen, are formed at the anode and the cathode, the gases will collect in the top of the test tubes and will displace the water downwards until eventually they're completely filled with gas. So here we have the graphite anode and a graphite cathode. Here we can see oxygen being produced at the anode, and here we can see hydrogen being produced at the cathode. So in order to do this, again, we can't really do it particularly well with absolutely pure distilled water, but by adding a few drops of dilute sulfuric acid, this actually can be done fairly well. So the electrolysis of pure water can be represented by this Ionic equation here. So at the cathode, we have the reduction of hydrogen to form hydrogen gas. At the anode, we have the oxidation of hydroxide ions to form oxygen gas and water. So another important electrolytic reaction that you need to be familiar with is the electrolysis of copper chloride in aqueous solution. So let's take a look at that now. Now, in this type of electrolysis, copper atoms are produced at the negative electrode and chlorine molecules at the positive anode. So how would you write a balanced equation to show what happens at the anode and the cathode? Well, let's look at that now. So at the anode, the chloride ions lose electrons to become chlorine molecules. So this is something that we've seen before. It simply looks like this. At the cathode, the copper ions in the solution gain electrons and become copper atoms, which are laid down as a solid deposit of copper metal. So again, let's take a look at how we would visualize this using an animation here. So here we can see the electrolytes. This is copper chloride in aqueous solution. We see the copper ions migrating towards the negatively charged electrode because they are electrostatically attracted to it. They gain electrons to form a deposit of solid copper. At the positive electrode at the anode, the negatively charged chloride ions, which are attracted to the anode, will give up their electrons to form bubbles of chlorine gas. Now, we can electrolyze another solution of copper sulfate. Now, this time we can use this reaction, as we saw before in where we looked at the extraction of metals and the purification of metals, to purify impure copper. So let's say we had a piece of impure copper and we wanted to purify it. Well, we would attach that piece of impure copper in an electrolytic cell and make it the anode, the positive electrode. The negative electrode, we use a thin strip of pure copper metal, and again our electrolyte is copper sulfate. So in the copper sulfate we have copper ions and we have sulfate ions. So what's happening here is that the anode will slowly lose mass because copper will dissolve into the solution as copper ions. Now at the cathode, those copper ions, which are positively charged, will migrate towards the negatively charged cathode because they have the opposite charge. They're electrostatically attracted to it. Once they touch the surface of the cathode, they will gain electrons to form a deposit of pure copper on the copper metal cathode. And by doing this, we can purify the copper that's in the anode and lay it down as pure copper here and leave behind any impurities. Now, if we were to electrolyze copper sulfate by using carbon electrodes, graphite electrodes, we would see something else happening. So when we electrolyze copper sulfate solution, again, we have hydroxide ions and hydrogen ions which are present as a result of the presence of water and its dissociation in this solution. Of course, we also have the Cu2+ ions and the sulfate ions from the copper sulfate. So in this reaction, oxygen gas is produced at the anode, and the cathode will gain mass once again as the copper ions attach themselves to the surface and gain electrons to form a solid deposit of copper metal. Now, as this happens, the electrolyte will gradually change to a dilute solution of sulfuric acid because we are losing copper ions, and what's left behind is hydrogen ions and sulfate ions. So at the anode, in this case, we have copper, which is giving up electrons to form Cu2+, so we're forming copper ions. At the cathode, we have copper ions gaining electrons to form copper metal. The amount of products which are produced during electrolysis will always depend upon how long the current is being switched on for and the amount of current that has passed. Now, electrolysis can not just be used to purify substances, and it can also not only can it also be used for splitting compounds into their elements, it can also be used for other applications, and one of those is called electroplating. So EPNS stands for electroplated nickel silver. So this nickel object has been plated with a thin layer of silver by means of electrolysis. Other metal objects can be plated with other metals such as gold, silver, copper, or other metals, also using electrolysis. So let's take a look at how we might use this process for what we call electroplating, how we can lay down a thin layer of a metal over another metal using electrolysis. So here we can see a piece of zinc foil being plated with copper. Now the way that we do this is by means of an electrolytic cell that looks like this. We have the metal cathode that we want to lay down the copper deposit onto the surface of, and we have an anode made up of impure copper. And again, the electrolyte that we're using is copper sulfate. So the anode is a piece of impure copper, and it's the copper from the anode that we're going to use to plate the metal cathode, or whatever metal object we're using as the cathode. The electrolyte is some solution of a salt. It doesn't have to be copper sulfate, it can be some other soluble copper salt. And the cathode, again, can be some piece of jewelry or an ornament that we want to plate with the metal from the anode. So the surface of the cathode, for reasons that we've seen already, will become plated with copper from the anode. So in this case, at the anode, copper ions, or rather copper atoms in the impure copper, are going into solution as copper ions because they are giving up electrons, they are being oxidized, and those electrons are then flowing into the circuit from the anode. Now, this forms copper ions which go into solution. At the cathode, those copper ions will gain electrons to form a deposit, a thin layer of copper metal over the surface of the object. Now, a similar approach is used to plate various objects with a variety of different metals. So, for example, chrome plating, as you can see here on these vehicles, is typically done by a similar process. We can also plate objects with thin layers of gold and silver by means of electroplating. So here we can see some gold-plated objects and some silver-plated objects which have been made by electroplating. Now, as we saw before, some metals can be extracted simply by thermal decomposition and then displacement reactions, but some other metals require electrolysis to be separated from their compounds. So copper, for example, can be extracted from a mixture of copper ore and carbon, and this reaction happens in two stages. First, the copper ore, called malachite, which contains copper carbonate, is thermally decomposed to form copper oxide. So we heat the copper carbonate and it turns from this green powder into black copper oxide, and carbon dioxide gas is being released. We can do this in the laboratory again by simply taking a crucible of copper carbonate and then heating it with a Bunsen flame, and we can actually observe the change in color as the copper carbonate decomposes to form copper oxide. The carbon dioxide is simply given off into the atmosphere. Once we've formed our copper oxide, we can then displace the copper from this compound by using a more reactive element such as carbon, and this will then form copper metal and carbon dioxide. Now, the copper produced by this reduction process is usually pure enough for most uses except for electrical components and wiring. To further purify the copper, it has to be made into an impure sheet and then used as the anode in an electrolytic cell, as we saw before, in order to purify it. Now, another reason to further purify the copper by electrolysis is that the impure copper plate typically will have other rare elements, such as gold, found within it, which can then be isolated after the electrolysis is complete. So once again, this is how we would purify copper by means of electrolysis. So we take our impure copper anode, connected in a circuit with a very thin sheet of pure copper metal as the cathode, and we use a soluble copper compound such as copper sulfate as our electrolyte. So the anode is a sheet of impure copper which is being used to plate the metal cathode, and the electrolyte is a solution of a copper salt such as copper sulfate. So we mentioned in a previous lesson that aluminium and titanium, because they are more reactive metals, typically they are separated from their ores by electrolysis, and this is an extremely expensive process because of the level of energy required, first of all, to melt the aluminium or titanium compounds in the ore, and then the energy required to do the electrolysis. Now, it's still economically viable to do this because both of these are highly desirable and economically valuable metals. They are both low in density and resistant to corrosion. Titanium also is extremely strong despite being very lightweight. So this makes these materials very useful in the aircraft industry and various other industries. Now, both of these metals are above carbon in the reactivity series, and so they can't be reduced from their oxides by means of a displacement reaction using carbon, such as we saw in the example of copper being displaced from copper oxide. This means that their extraction is expensive, and again, this is because there are many stages in the process and it requires a large quantity of energy. So we saw in a previous lesson how we extract aluminium. It is done by means of electrolysis. Now, aluminium smelting plants therefore require enormous amounts of electricity, and typically they will have their own power station in order to supply that electricity constantly. So many of these aluminium smelting plants are located next to ports and also next to hydroelectric power stations, like near dams. So, aluminium is extracted from its ore, which is called bauxite. Bauxite contains a large amount of aluminium oxide. So the aluminium is formed at the cathode. So the cost of electricity is actually a major factor in the production cost of aluminium. So the equation for the extraction of aluminium starts by taking aluminium oxide and then melting it so that you get aluminium ions and oxide ions. At the cathode, the aluminium ions will gain 3 electrons each to form aluminium metal atoms. At the anode, the oxide ions will gain electrons to form oxygen gas. So the overall reaction is that aluminium oxide is broken down into its elements, oxygen gas and aluminium. So once again, here is a diagram of the electrolytic cell which is used. To achieve the high temperatures necessary to melt the bauxite, it is mixed with another substance called cryolite, which reduces the energy requirement to do that. So here we can see a solid crust of aluminium oxide forming near the surface where it's cooler. We have the carbon anode, which is here. It's made of graphite. And again, this is because the temperatures in here are extremely high and graphite is resistant to high temperatures. Nonetheless, the carbon anode will degrade over time. It will oxidize. It will react with the oxygen gas being produced. And so another reason why this process is expensive is because the carbon anodes have to be periodically replaced. Now the cathode, the negative electrode, is actually the lining of the entire electrolytic cell, as we can see here. So, around this assembly you have electrical and thermal insulation, and here we can see at the bottom molten pure aluminium metal is being produced, and this can be tapped and drained away. So, electrolysis for the extraction of aluminium from its oxide and also the extraction of titanium from its oxide can be extremely expensive. It requires a lot of electricity. So again, for this reason, aluminium smelting plants often have their own power station built nearby to provide that electricity as cheaply and as abundantly as possible. Again, the other major component of the cost is the energy required to heat the electrolyte to a temperature where it becomes a liquid. And the temperature required is about 900 degrees centigrade. We can reduce the amount of energy required to achieve this by mixing the bauxite with cryolite. Again, as I've said before, the anodes are also slowly corroded by the presence of oxygen, which reacts with the carbon in the graphite anode. So the constant replacement of the anode also adds to the overall cost of the production of aluminium from its ore. So again, we can visualize this in a simplified manner. Here we can see at the anode, oxide ions are giving up their electrons to form oxygen molecules. At the cathode, aluminium ions are gaining electrons to form aluminium. So again, this is a kind of simplified representation of the way that this works. So let's take a look and finish off here by looking at the ionic half equations for the electrolysis of the following molten substances. We've already looked at aluminium oxide. Let's also take a look at lead bromide, lead iodide, and potassium chloride. So aluminium oxide we've already seen at the anode. Again, for every 1 unit of aluminium oxide, we have 3 atoms of oxygen, and we have 2 atoms of aluminium present. Now, these are actually present as ions. So if we consider what's actually happening here, we have 6 oxide ions giving up a total of 12 electrons to form 3 molecules of oxygen gas. At the cathode, those 12 electrons are supplied to a total of 4 aluminium ions to form 4 aluminium atoms. Now these will be in the liquid state. So the overall reaction is 2 molecules of aluminium oxide forms 4 atoms of aluminium in the liquid state and 3 molecules of oxygen gas. Let's take a look at the electrolysis of lead bromide in the molten state. So at the anode we have 2 bromide ions, each of which give up 1 electron to form a molecule of bromine. Now this will be in the gaseous state. Now these 2 electrons will flow around to the cathode where they will combine with 2 Pb2+ ions. This, or rather 1 Pb2+ ion. This will form an atom of lead which will be in the liquid state. So in this case the overall reaction is lead bromide forms lead liquid and bromine gas. So again we see the ionic half equations for the electrolysis of lead bromide here. Let's take a look at what happens when we look at lead iodide now. So lead iodide at the anode, we have 2 iodide ions, I-. These will each give up 1 electron to form 1 diatomic molecule of iodine gas. These 2 electrons flow into the circuit around to the cathode where they are accepted by one lead ion, Pb2+, to form one lead atom. And so again, the overall reaction here is lead iodide forms lead and iodine gas. So once again, we can see how we construct that half equation for this particular compound. And finally, let's take a look at potassium chloride now. So potassium chloride, at the anode, you have chloride ions, each of which will give up a single electron. 2 chloride ions will give up a total of 2 electrons to form one diatomic molecule of chlorine gas. And at the cathode, those 2 electrons will be added to 2 potassium ions to form 2 atoms of potassium metal in the liquid state. So in this case, the overall reaction for this electrolysis is shown here. Okay everyone, that's going to do it for this lesson. I hope that was useful to you. As always, if you have any questions, go ahead and type those in either the live chat for this lesson on the lessons page, or send those to me as private messages. Now I'm going to get into the Q&A discussion with the students that have been patiently waiting with me via Zoom. Thanks for watching, and I'll see you in the next one. Take care.